Hi, everyone. Welcome to the ECSS Symposium. Sorry for the delay this month. Our first speaker is going to be Syed Koric from NCSA. Syed leads NCSA's private sector program and was involved in XSEDE and ECSS at one time, but isn't currently. And so I want to thank him for agreeing to give this talk, even though he's not funded by the project. I think there'll be a lot of interesting things we can learn from some of the work that's been done in NCSA's private sector program. And appreciate him taking the time to prepare for this talk. So, Syed, if you want to go ahead and take it away, can you see your slides on the conference?
I see on my laptop, but people who are in the room, they don't see it on the projector. So if we go on like this, maybe Jay can do something. It's his laptop. Thanks.
Okay. Well, they should. So for other folks who are on the web conference, can you see my shared desktop?
Oh, it's decided.
Yes, we can.
Okay. So other people on the line besides people at NCSA can see the slides.
No, I'm not allowed in.
Oh, okay. There we go. There we go.
It decided to switch modes on me. I'm sorry. I don't know why. I'll make it a full screen. Okay. I think we're as good as that.
Yeah. Well, we're going to be missing a little bit.
Yeah. Desktop.
There is a part.
That's okay. That's good enough.
Lower part of the slide.
Yeah, I wonder if she puts it in slideshow. Hey, Nancy.
Yep.
Is PowerPoint in slideshow mode?
No, because it's a PDF.
Oh, okay, never mind.
And it's not even accepted as a format to upload the slides to ReadyTalk, so I'm sharing my desktop with the PDF.
Oh, that's just fun.
Yeah. Okay.
Okay.
All right. Maybe I can start.
Yep. Sounds great.
We see about 3/4, missing the last quarter, the bottom part, but I hope everybody else can see everything. So anyhow, as Nancy said, thank you everybody for inviting me. I have been, Nancy, I can see a little bit more now, almost everything.
Sorry, quick interruption. Nancy, you can do full screen, view full screen.
Okay.
Okay.
I think it's okay now, Nancy.
In the preview, you can go to full screen mode. In the preview window up, view full screen. Oh, sorry, in the view menu.
Okay. All right.
Yeah. Either you can do the slideshow. Yeah, probably the slideshow, the last one.
Oh, okay. Thank you, Suresh.
Yeah.
Much better. Thank you.
Oh, much better. Thank you.
Thank you, Suresh. Okay, take it away, Syed.
Thank you for suggestion. Okay. Anyhow, just a slight correction. I'm not leading the private sector program. I'm actually technical lead here, but there are business people who are leading the private sector program in NCSA. Anyhow, so I'm going to be talking about some of my previous engagement with XSEDE, and then we'll briefly touch on some work that I do on Blue Waters right now, and some of the industrial engagement that we have here in NCSA. So maybe if you can switch to next slide, please. Okay, so here's I understand, people don't want to hear too much about the science, so there was a lot of science in this one. That was a ECSS project, with the title of 3D Study Elastic Plastic Transition and Fractal Patterns in 1 million grain cube of grade, which was a material was steel. So if you think about this 15 years ago, that would be a big domain. It's not a big domain anymore, but what is interesting here is that every single element in this domain, and there are 1 million of them exactly, has a different material properties. So that means we were really looking at the non-homogeneous material, and if you look at the material in nature, even in manufacturing, they all have some kind of distribution of material properties inside, we really look at this phenomena, how much they are non-homogeneous, and then from there, we look at the transition between elastic and plastic behavior, and we derived some interesting theoretical observations there, and this was all published at the Philosophical magazine, which is one of the largest, one of the oldest technical journal in the world, and that was published last year. And the whole project lasted from, I believe, 2012 to 2012. This was with Professor Star-CCM here from University of Illinois, and this was a ECSS project. Right now, I'm not going to, again, spend too much time about this. We can probably spend 10 or 15 slides about that. But what is important, we are aiming at much larger simulations now on blue waters with this project. And also, this was success in the terms that we got seed money from IACSEDE, which is our Illinois Advanced Institute for Computation, to continue with this project. So this was a real true spirit of ECSS project, which kind of used as a pilot project, to demonstrate things, and then, to go on with the funding and more funding. Okay, thank you. Next one, please. So this is our blue water system. I'm pretty sure everybody on the call knows what blue water is. Three things here. We have usable storage bandwidth is over 1 terabyte per second. We have usable storage of 25 petabytes. I lost my screen right now, unfortunately. So Jay is fixing it.
Keep talking.
Keep talking. Okay, and we have over 380,000 integer cores there, floating point integers there, and they are all AMD. The system itself is situated in a corner of our campus, and the building by itself is also a miracle. So next one, please. So this is another system. This system is dedicated for our industrial partners only. This system was bought by NCSA internal money, and if you guys think that we are making big profit with this system, no, we don't. The regulations here in the state of Illinois are very strict. We are not allowed to make any profit with this system. It's just for the investment recovery and for our salaries. And this is used actually for exploration for our industrial partners to give some kind of, and our industrial partners are big manufacturing companies, mostly here from Midwest area. So this system is actually is used, is a playground for them to explore things, before they actually either decide to have similar system internally or continue computing with us on a bigger system. So right now, iForge, which is the name of this system, has over 2,000 Sandy Bridge cores. So in essence, it's very similar to Stampede system. We don't have any GPUs there, but we have very resilient shared file system, which is GPFS, and we have QDR infinite band right now as an interconnect, but we are looking, this system is supposed to be evergreen, so we are already looking in the next generation of Intel processors, which is the Ivy Bridge, to upgrade this system and also to move to better interconnect, which would be probably FDR instead of IBQDR. So what is interesting with this system is actually it's up 99% of the time. So if you are really talking about industry and people who are using this system, they like this. The system is up 99% of the time. Next one, please. So now I'm going to be briefly talking about one of the projects that I'm involved. This is the project which is doing evaluation of massively parallel linear solvers in implicit FEA, and this is partly funded by industry. You guys know that implicit finite element code spends 70 to 80% of the time actually calculating, getting a solution of a sparse linear system AX equal B, where A is very sparse and B is the right-hand side, which is usually not sparse. And where is this pretty much wide range of applications from solid mechanics, computational fluid dynamics, and if they are using finite element method, implicit finite element method, reservoir simulation, very important for people who are doing oil and gas, circuit design, linear programming, and etc. Next one, please. So this is a kind of presentation. What I'm talking about, you see some part which is highly refined, meshed, some mechanical part, and on the right-hand side you see how this part matrix looks like. In a typical finite element application, you can see that all the non-zeros are pretty much bunched up on the diagonal, and they are usually symmetric positive definite, so you can look at the other side of the diagonal, you will see the same. But we are usually just storing the lower triangular part of this big matrix. Next one, please. So where are the matrices which are used for testing are coming from? So they originate either from in-house industrial and academic codes or from a commercial FEA codes. The one that we work most of the time is actually an STRAN code. An STRAN code is allowing us actually to extract those global system matrices, for this kind of testing. These systems, again, are symmetric positive definite. Usually, so the nominal size is 1 to 20 million, and the number of non-zeros varies from 120 to 500 to actually 500 million of these non-zeros. What is important here, condition number, which is a condition number of the matrix, which is telling us how much ill conditioning is happening there, how solvable they are. So they are ranging from 10 to the 3 to the 10 to the 12. Next one, please. So what are the solvers that we are testing? Most of them are actually publicly available, except the first one. First one is WSMP solver, which is from Watson, IBM, same guys who beat Jeopardy on Jeopardy 2-3 years ago. SuperLU from LBNL, MUMPS is from Europe, Hyper and PETSC, and pretty much everybody is familiar with them. And then we have some commercial finite element code. We are testing them too, and these things are under NDA. We are not allowed to say which one. Next one, please. So here's a comparison, for example, for the execution time. Here you have a comparison between typical iterative solvers like conjugate gradient in PETSC or PCG in Hyper versus direct solvers like MUMPS, WSMP, and SuperLU. And you can see, that in this particular case, WSMP from IBM, having the best scaling and best wall clock times. So the conditioning is 6.9 10 to the 4. So I would say it's a small or moderate ill conditioning. Now the next one, please. The next one now, we are really talking about big matrix, big system. So this system is 20 million. It has 827 million non-zeros inside, and the same domain as the previous one. We just refined more with the free meshing with tetrahedral elements, and that contributes to more ill conditioning. So now the condition number is 10 to the 7. And you can see what is happening. Pretty much the iterative solvers that we are teaching kids usually, when you have big matrix, use iterative solver. Well, iterative solver is fine as long as it goes, but when it comes to ill-conditioned systems, they need lots of iteration before they converge to a good convergence, to a good accuracy. While direct solvers like WSMP, doing factorization right away, sparse factorization, you can see the big difference, how well, for example, the sparse solver from IBM is actually doing all of this. Of course, on the downside, direct solvers are using much more memory. So, this was on iForge. iForge, as I mentioned, has 128 gigabytes of memory per node, so it could fit this matrix, with factorization. Next one, please. So this is comparison between previous incarnation of iForge, which was with Westmere and the current one with Sandy Bridge, and you can see pretty much the difference. If you engage XAVX, SSE extensions in your compiler, you can see, how much gain you can get, So this is the higher, the better. You see the performance here of WSMP. You can see, how much we almost get 5 teraflops, on 960 threads on current iForge compared to the previous one. Next one, please. So this is a commercial finite element package. You can see this is Abacus from the SALT system. You can see, where the state of the art for this kind of scaling is. So this matrix is 30 million degrees of freedom. This was again compute on iForge. Number of cores were varying between 24 and 196. And in this particular case, the company that sent this input file for this simulation, they needed about 7 hours, while we demonstrate here that this simulation on iForge can be done in 1 hour, which is a game changer if you are really industry and under some kind of deadlines and pressures, to deliver these and get some better design as soon as possible. Next one, please. So now I'm going to be talking, moving gradually from iForge to Blue Waters. We have a really good story there in the explicit finite element area. So here we were few months ago, as Blue Waters was coming online, we were working really diligently with Cray and also with ISV, which is a explicit finite element vendor, LS-Dyna from which is a spin-off from Lawrence Livermore, and PSP partner, which is in the big OEM, company under NDA. We can't say which one. So the company provided real geometry, load boundary conditions, and we are simulating highly nonlinear transient dynamic problem with difficult contact conditions. MPP-Dyna solver was fully ported and optimized to create a Linux environment, which is very important. If you look at Blue Waters, there is a so-called CCM mode, cluster compatibility mode, where they are emulating typical Linux environment, cluster environment under Cray, and this was done for the binaries that don't have support of Cray. And these things go again as far as they could, but if you want to go to extreme scaling, they have to really port directly to Cray Linux environment, which we call CLE, and taking full advantage of the Gemini interconnect. Next one, please. Now, you see the scaling that we actually achieved. First, good old iForge, the red line, doing pretty good, having Sandy Bridge being faster than AMD in Interlagos. You can see pretty much, having better wall clock times up to, let's say, 1,500 cores. And then what is happening, the Gemini interconnect on Cray is taking off, and as we are going wider, as you will see on the next slide, there is more and more communication. And you can see that the MPI solver of LS-Dyna scaled really well on 3,000 cores. And lately, actually, LS-TC come up with a hybrid code, which is a combination of MPI and OpenMP. And in this particular case, we hit the scaling all the way to over 8,000 cores, which was the highest known scaling on LS-Dyna to date. Next one, please. So this is what I was talking about. If you look at some kind of profiling of the code on a smaller scale, on a 64 cores, you can see that everything is dominated by computing, and that's why Sandy Bridge being better processor than AMD Interlagos, you saw that iForge is really ruling there. But as we are going wider, for example, to 512 core in this case, and wider, you can see that communication is becoming dominant. As communication is becoming dominant, the interconnects that you have is actually making difference, and that's why I see that Blue Waters is really doing there better, much better actually. The next one, please. So what do we do now with this project? So we are getting even larger problems. As we are getting larger problems, we are hitting all kinds of problems there, as you all know, as you are increasing the problem size, we are hitting some kind of limits of the code and also the hardware. In this particular case, we have only 64 gigabytes of memory per XE6 nodes of blue orders, so it'll be great if we have actually 128, and then we'll be able to fit. So we are trying to get to some tricks, how to do decomposition distribution on a fashion that can fit 64 gigabytes of XE6 nodes of blue orders. Of course, hybrid MPI OpenMP solver uses less memory and less communication. It's in the development. And what is important, when you are really going over 8,000 cores, load balance and contact and rigid body algorithms are really important. The next one, please. So here's a brief example of on a CFD side, also in a commercial code, Star-CCM, which is one of the leading CFD codes. Again, another partner, not the same one. They provided transient turbulence, single-phase compressible flow, and we run this on blue orders. So again, complex real live production case, very important to say. So this is coming directly from industry, not from ISV, not from the software vendor that they tend to give a simplified geometry, simplified physics, So this is a real stuff. Next one, please. So here's again similar story. You see the red line. You see that here higher is better. So you see that this is a number of iterations per 1 hour of simulation. So you can see that up to 256 maybe, iForge is doing better job because of the better chip. But then as we are scaling wider with more communication, you can see, that blue orders pretty much take off, and we hit about 2048 cores before we got some partitioning problems coming from the Star-CCM, and I guess, they haven't scaled so wide yet, so, we are talking to them now, and see, if they can improve this partitioning, to actually do partitioning more than 2,000 cores. Next one, please. So what is the future of HPC? I believe, the future is actually in GPUs, especially. I wasn't a big fan of GPUs not so long ago, but with OpenACC, we really see, that porting with OpenACC is very similar to OpenMP, and things are fairly easy to be done, versus CUDA stuff that I was never a big fan of. So I'm giving an example here, so you can see the comparison between blue orders having XK7 with Interlagos and GPUs, the Kepler, of course, the newest one from NVIDIA, versus I had a count on Keeneland, which was a initial deployment system at Georgia Tech, and I understand they have a better one now, but at that time that was Westmere with Fermi GPUs, and you can see pretty much what is happening with the Laplace 2D code. In terms of wall clock time, lower is better, and you can see OpenMP is doing a relatively good job, maybe scaling too, but then as you are actually engaging the GPU code with OpenACC, you can see, at least on blue orders, we come up to 14,000 speed up compared to serial execution. So you can see right away the impact of GPU with OpenACC. And we just have to change a few lines there, to accommodate pragmas of OpenACC versus OpenMP. Next one, please. So for a long time, the GPU was pretty much bounded to the node. So now GPU computing, especially with OpenACC, works very well between the nodes too. It's in kind of hybrid fashion with MPI and OpenACC. And you can see, again, the ISV vendor, at least in the finite element area, that's paying most attention to GPUs from day one was, again, Simulia Abacus from the Salt Systems. And you can see what we have right now. You can see the comparison between Cray XE6 that have only CPUs and Cray XE7, again, that I mentioned in previous slide, that have CPU and GPU. And as we are going out of box, you can see, there's still scaling with GPUs, so and it's significantly better, especially in the area of 64 cores, there was a GPU is really accelerating the code. The next one, please. So just a couple of slides, and I'm going to be done. So this is the initiative from U.S. Council of Competitiveness. I'm just giving you an example of the industrial engagement that we have. It's called NDEMC, which is National Digital Engineering and Manufacturing Consortium. So what is behind OEMs, big boys, manufacturing like Caterpillar, John Deere, Boeing, they all pretty much handle high performance very well, and they do very well with high performance. But their suppliers, which are small and medium-sized companies, which we call SMEs, they don't necessarily speak language of modeling simulation very well. So especially in HPC. So the idea was actually to bring modeling simulation to supply chain, to small and medium-sized companies, to them. And this regional pilot of NDEMC started in fall of 2011 in the Midwestern supply base, and NCSA, the private sector program, and NCSA is an integral part of that. The next one, please. I think that's the last one. So here's an example of NDEMC project. So the company is from, I believe, South Dakota. They have maybe 30 to 50 employees, and they are producing these charge air coolers. Charge air coolers are used actually when you are when the air is leaving, for example, in a big diesel engine, when it's leaving turbocharging and going into engine back. We are doing some kind of cooling there in order to actually increase the efficiency of the engine. And that particular part is going through cycles of thermal loads. For every cycle, there is a thermal load which is going up and down, and that's generating thermal strains. As they're generating thermal strains, we are going through cycles of fatigue after a certain number of cycles. So one would naively think, small company having this kind of product, they don't need the simulation and modeling, but they actually turn out that this simulation is very sophisticated. And even though the company is small, the challenge was not small. So the objective was to study fatigue life of the charge air cooler. And in order to properly do that, it has to be three-step sequential coupled simulation, starting with the CFD simulation of the turbulent fluid flow through this heat exchanger with a vector heat transfer, which then at the end provides the boundary condition for the finite element analysis for the solid part, and then go to finite element analysis of the thermomechanical parts, which provides transient thermal stresses in solid part, which is history, some kind of history of the stresses in this part, and then you plug these history of the stresses in some kind of fatigue model, and then you can actually estimate the cycle life of the critical points there. So again, we did this here at NCSA for an SME, and that was a really successful story. Next one, I think that's the last one. So special thanks for this talk. I'm hoping actually I'll give you a little glimpse, what we do here in the PSP part of the NCSA. Professor Martin Star-CCM from Mechanical Science Engineering Department, he's the one. He was the PI on my XSEDE project. Dr. Ahmed Taha is doing CFD at NCSA, and Cray, and two PSP partner companies which are both under NDAs. NDEMC consortium, LSTC is the ISV that we are working with LS-Dyna. IBM Watson, very helpful. They the WSMP code is the library, solver library is actually commercial, but they allow us, to use the license, for this kind of project. And then ISV, which is similar the solve system for Abacus, and of course my colleagues from Blue Waters, what I'm working with all the time. Thank you.
Sayed, thank you very much, and I apologize once again for the delay in getting started today. For folks on the call, do we have any questions for Sayed? I was kind of,
we have here Sudhakar.
Good, thanks. Go ahead, please.
So this course,
you'll have to speak up, though, or repeat the question.
So do you have communication hiding in this course? Or is there a way to reduce the communication at a higher core count?
You mean LS-Dyna code?
The total code, it looks like the communication is going to affect.
Yeah, that's very difficult. As you are trying to scale wider, of course there's more and more communication and less computation. It's a general pattern especially for engineering applications. And
you can't hide the communication behind computation.
Well, again, you are partitioning the domain in a sense, that as you are partitioning domain, they have to talk to each other, and they usually talk to their neighbors, but they are also sometimes talking to cells which are pretty far. So reducing communication, there are probably tricks to do that, but I think here we are really talking about ISVs, that have pretty much sophisticated level of programmers there, and they know code better than anybody else. So I think this is as good as it can be in terms of hiding the communication. So really, we come to a point, where actually you have to work something like with interconnect, and you can see that interconnect in this particular case, the proprietary interconnect from Gemini, actually makes a big difference. Anybody else?
I think in the interest of time, we'll go ahead and move on. It's interesting. When I first started at SDSC, I was the industrial contact also, and LS-Dyna was one of the codes then, and that was 20 years ago on the Cray YMP. So it's interesting to see that it's still well used.
Yeah, and look at you, Nancy, now, and look at me. I'm just kidding.
You're doing much better.
All right, thank you, guys.
Thank you, Sayed. Thanks very much. Our next